It's okay. Okay, let's start this our seminar of today. Okay, today our IAU the local university seminars. We are very happy to have the speaker Paolo Sakura. He is the first researcher in the INAF-Milan Observatory, I think. His research interests mainly focus on the galaxy evolution also he argues using various methodologies. His primary goal is to reconstruct the mechanisms of the galaxy mass assembly by studying the dynamical and stellar populations, properties, and intermediate and high redshifts. And since 2021, and he has been principal PI of the SHARP, ELT SHARP project, which is an ambitious project I also involved when I was in Padua. Which he conceived a near-infrared spectrograph designed for the ELT to overcome the limitations of future instruments currently under design. He is currently leading the conceptual and feasibility development of the next generation instrument. Okay, let's start, Paulo. Please take away.
Okay, thank you very much, IFN1. And I am happy to be here today, and thanks for giving me the opportunity to present, to introduce SHARP. I will try to share, sorry. No, share the screen.
You can share screen. Okay.
You see
Yes.
the screen?
Yes.
Okay. Okay, perfect. Oops. Hide.
Cancel.
Where is, sorry. How to hide? Okay. Okay. Well,
Okay.
I am happy to be here. I can put down this one. And thanks again for giving me the opportunity to introduce SHARP, an advanced near-infrared multimode spectrograph. Actually, it is a concept study of a near-infrared multimode spectrograph for the ELT. This is the layout of my talk. First, I will introduce what is SHARP, and we will see also what is the near-infrared spectroscopic facilities expected in 2030s, and the rationale behind SHARP, why basically we propose SHARP. Then we will see what is the main properties and capabilities of SHARP, and some of its application to the science, to some scientific cases relevant for the local universe. And finally, I will show what is the project status and prospects. Okay, what is SHARP? SHARP is a near-infrared multimode spectrograph. Sorry, do you see the upper bar? The black upper bar on top of the screen.
We can show.
Do you know how can I move these or remove this one?
Please have a try. Let me check.
Okay. Okay. This is basically SHARP is a near-infrared multimode spectrograph conceived to exploit the ELT aperture, both in terms of the finest reachable fluxes and the sharpest angular resolution over the widest adaptive optic corrected field. SHARP makes use of a multi-conjugate adaptive optics module The MCAO is a unit corrector for atmospheric turbulence, which provide a uniform correction over a wide field of about 2 times 2 arc minutes, as for instance Morpheo, the MCAO system planned at the ELT. SHARP is composed of 2 main units, Nexus, which is a multi-object spectrograph with a configurable slit system, and VESPER, which is a multi-integral field unit. SHARP works over the wavelength range between 0.95 and 2.45 micron. And we are going to propose SHARP to the next ESO call, Expanding Horizons. And we will see something more about this call at the end of this talk. What is the properties of SHARP? Nexus, the multi-object spectrograph, cover a wavelength range between 0.95 and 2.45. The field of view is 1.2 times 1.2 arc minutes, over which can be deployed up to 30 slits, considering a slit length of 2.4 arc second. The pixel size is 35 milliarc second. These are the resolutions for extended source, while for point source we can reach a spectral resolution of 17,000. VESPER is a multi-IFU, which works over a slightly narrower wavelength range between 1.2 and 2.4 microns. It is composed of 12 probes that we call field selector, each one having a field of view of 1.7 times 1.5 arc seconds, sampled by a spaxel of 31 milliarc seconds. These 12 probes can be deployed over an area of about 24 times 70 arc second. And these are the resolution for extended and point sources. On the right, it is shown a schematic view of SHARP, basically the light coming from the MCAO, for instance, Morpheo, pass through an atmospheric dispersion corrector, which correct again the light for the atmospheric dispersion. These units communicate to Morpheo the position of the natural gas stars to correct the optics and correct the field for the atmospheric turbulence. The light enters in SHARP, and here, around here, there is the MCAO focal plane over which there will be the unit selector system with, that switch the light between VESPER and Nexus. Here I summarize the spectrograph expected in the 2030s. Basically, without entering in the detail of each of them, what I would like to show is that basically near-infrared spectroscopy, the standard of the near-infrared spectroscopy, is fixed by JWST. It provides a multiplex of about 100 spectra at a time as multi-objects in the multi-object spectrograph mode, thanks to the microshutters array, even if it has some strong limitation, as we will see later on, and provide also integral field spectroscopy with through a monolithic single IFU. The angular resolution is 0.1 arc second, and its mission likely ends between 2035 and 2040. And what I would like to underline is that none of the planned spectrograph is able to follow the path opened by JWST. Indeed, the first light instrument, Mikado, at the ELT, which is an imager but also a spectrograph, provide long slit spectroscopy within a slit width of smaller than 50 milliarc seconds. Hence, it is a spectrograph thought for best suited for point sources. Harmony is a single eye view, again provide spectroscopy for single object, and its starting date is not yet defined, while the other two spectrograph, Andes and Mosaic, are both limited to 1.8 micron, since they are fed by fibers. And Mosaic is supported by basically a poor adaptive optics system, providing a resolution of about 0.15, 0.2 arc second at most. And while Andes provide eye view observation within an extremely small field of view. Indeed, Andes is thought to study the atmosphere of exoplanet. And for comparison, these are the properties of Nexus and Vesper of SHARP. Let's see why SHARP. That is to say, what is the scientific rationale behind SHARP that justified these characteristics and these properties. First of all, basically most of the fundamental questions here summarized basically deal with the more general topic of understanding how baryons assemble to form stars, galaxies, and structures, and how they evolve over cosmic time to appear as they are today. Some of the key questions are, for instance, the origin of the globular clusters and the origin, that is to say, their formation, and also the origin of the multiple stellar population observed in some of them. What physical processes determine the shape of the initial mass function? What is the physical motivation of the transition between low mass and high mass stars? What is the origin of the galactic bulge, whether it is a classical bulge or a pseudo bulge? And what is the mechanism that keep quenched a galaxy, also for instance the Milky Way, in spite of the large amount of gas? And what regulates the quenching of star formation, both in the low redshift and in the very high redshift galaxies? Of course, what are the extreme physical conditions governing the star formations apparently dominating the very early some of the galaxies at very early universe, and what is the dark matter fraction in galaxies, both at high redshift and in the local universe, whether the fraction has evolved, has changed along the time or not? And what is the physical interplay between black holes and galaxies? And where is the elusive population 3 of primordial stars? Thus, understanding how baryons actually assemble to form stars and the other structure can be tackled through the information basically fundamentally stored in the spectra, in the atomic emission and absorption line. Such atomic emission and absorption line can be observed in the local universe in star-forming environments where the baryons assembly takes place. However, these regions are often highly extinguished by dust and, of course, also crowded. And for this reason, near-infrared is essential for seeing through the dust. And of course, it is also needed a high angular resolution for resolving individual sources. But near-infrared is not only fundamental for the observation in the local universe, but also for high redshift universe, because of course, the wavelengths are redshifted Here are shown, for instance, the observed wavelength of some of the most important features, sampling the stellar content, absorption lines, and emission lines, gas content, as a function of redshift. The blue line marks the limit, the wavelength limit of Mosaic and Andes, 2 out of the 3 spectrographed at ELT, and also moons at VLT. And we see that basically such kind of limitation to 1.8 micron limit our study of extragalactic sources at redshift 1.5. And near-infrared extension up to the limit where the transmission of the atmospheric transmission is still high and the sky emission can be still efficiently removed is necessary. That is to say, up to 2.4, 2.45 micron, in order to observe, to can study over the entire cosmic time the properties of galaxies. And what is the angular resolution needed? Basically, in order to compare the main features of the high redshift galaxies with the local one, and to compare regions where baryons assembly takes place, we have to consider at least giant molecular gas clouds. Their size is about 150 to 100 parsec, and they contain up to 10 to the 6 solar masses of molecular gas. Hence, they are the main star-forming units, the main metal production units. They trace the galaxy rotation of a galaxy from which to derive the dark matter fraction. Most likely, they are cradles of globular clusters and hopefully also of primordial population 3 systems. In this plot on the right, it is shown the linear size attended by angles, in particular an angle of about 30 milliarc second in blue, the blue line, and in red, the linear size attended by an angle of 0.1 arc second, which is the angular size, the pixel size of a near spec. These two angles are as a function of redshift, and we see that an angular resolution of about 30 milliarc seconds samples very well the giant molecular gas clouds over the entire cosmic time. At the same time, it is worth to note that giant molecular gas clouds are not resolved by JWST for redshift larger than 0.1. So this is the reason why we have to reach at least an angular resolution of about 30 milliarc second, which is the resolution reached by SHARP in both observational mode, multi-object and multi-eye view. Let's see some details of SHARP. The black circle represents the focal plane of Morpheo, the MCIO, corrected for atmospheric turbulence thanks to the 6 laser guide star represented by the purple circles and by the 3 natural gas stars, which is used by the optics by Morpheo to correct the field for atmospheric turbulence. On this focal plane, it is placed the unit selector system, the system which switches the light between Vesper and Nexus. The field of view of Nexus is shown by the blue square, 72 times 72 arc second, while the red square, the red rectangle represents the field of view of Vesper, the field over which can be deployed the 12 probes of Vesper. Vesper is a modular system, and here are this field is the results of 2 modules, 2 contiguous modules. This is just one module, so one module comprises 6 probes, that we call field selector. The probes are aligned along the x-axis and can be moved along the y-axis to match the position of the target of interest for observation. The movement along the y direction is compensated by two moving mirrors to keep constant the distance, the optical path between collimator and camera. In this way, all the six probes focus on the same focal plane. That is to say, they share the same focal plane. And onto the focal plane, they form a strip of sky like this one. Onto the focal plane of Vesper, there is the slicer, which slices the image at 31 milli-arcsecond. Onto the focal plane, there is also the configurable slit system of Nexus, the multi-object spectrograph, in which the slit is formed by two bars which moved toward each other up to the position of the source. Here, as shown on the right, it is shown a zoom in of two bars which centered on two targets. For comparison, it is shown in the lower image the microshutter array of JWST. We can see, first of all, the microshutter has a slit width, a fixed slit width of 0.2 arcsecond, and there is no possibility, of course, to center all the sources within the shutter because it is a fixed, the microshutters follows a fixed pattern. On the contrary, Sharp can, on Sharp, the configurable slit system allow a perfect centering of the source. But this is not the main feature of Nexus. Let's see. Let's suppose that we are interested in deriving the fraction of the dark matter fraction in galaxies, and we selected our target galaxies like this one, and we are so lucky that all of them can be centered in the microshutter or NIRSPEC. In order to derive a rotation curve, we should align the galaxies along the microshutter, and we can do this just for one of them by rotating the field of view of NIRSPEC. On the contrary, Nexus will be able to align all the galaxies along the slits thanks to the inversion prism that will feed each slit. The inversion prism, here are shown a scheme, an optical scheme. This is a Pechan prism composed of two coupled prism, in which the light enters, coming from the field, enters from above with the green light on the right. After some reflection, 5 reflection, the light exit below with the green light on the left. That is to say that the field has been inverted. This implies that by rotating by an arbitrary angle the prism, the field subtended by the slit will be accordingly rotated. And this makes Nexus really unique. Here is shown a scheme of the optical design of the optical element of Sharp. This is the entrance window of Sharp. This is the focal plane of the MCAO of Morpheo, over which there is the unit selector system. The unit selector system is shown here on the right. On the basis, the unit selector system is composed by both the configurable slit system that can be seen here and by the integral field selector. These two elements can be moved since they are on a movable table, and according to the fact that the light coming from abroad is intercepted by the integral field selector or by the configurable slit system, the light will be deflected toward the module of Vesper, in the left and the right of this figure. Otherwise, we'll proceed through Nexus. This is the first optomechanical design of SHARP by Mahmoud and collaborators, by our engineer. And okay, let's see what can be the application of science, the application of SHARP for some science cases in the mainly focus on the local universe. Before showing the science case, I would like to spend 2 words in defining better the plot we have seen in the beginning. Here are shown again the linear size versus the redshift. The linear size obtained by the pixel size of SHARP, basically 30 milliarc seconds, as a function of the redshift and in logarithmic scale. These allow us to better understand the true linear size, the physical scale that can be resolved in the local universe. For instance, here is shown Andromeda M31, which subtend an angle of about 70 kiloparsec, 60 kiloparsec. And at the distance of Andromeda, we can resolve region inside them, inside the M31 of about 0.1 parsec. The red line represents the pixel size, 31 milliarc second, and all the scales below the red lines cannot be resolved by SHARP. On the contrary, all the scales above the red line can be sampled by SHARP at 31 milliarc second. Okay, let's start considering the comets composition. Comets, frozen fossil from the solar system formation, and hence they can provide fundamental insight into the physical and evolutionary processes that shape our planetary system and hopefully also other planetary systems. Here is shown Vesper is ideal to investigate the processes that related to comet activity. Here are shown the field of view of one module of Vesper with 6 probes, one of them pointing the nucleus, other 3 probes, for instance, the coma, and the remaining 2 probes pointing the ion tail. These allow us to simultaneous observation for nucleus, coma, and tails, and providing us with fundamental information. And finally, to retrieve how the ices and dust are stored in the nucleus, and hence how planetesimals formed in our protoplanetary disk. Another example is to unveil the origin of the central bulge of the Milky Way of our galaxy, whether it is a classical bulge or a circular disk evolution. And here are shown the 2 schemes, the two scenarios, and these can be in principle distinguished and resolved by near-infrared observation with SHARP Nexus, which allow to obtain single objects observations, single point source and stars observation, deriving both the chemical and dynamical information to disentangle between the two scenarios. Another application deals with what causes the Magellanic Stream, whether it is due to tidal interaction between large and small Magellanic Cloud, or rather it is the result of a combination of ram pressure and collision. Also in this case, Nexus can provide multi-object spectrograph for single stars, point sources, while Vesper can map the ionized gas and the high velocity clouds, and providing us information to disentangle these, to distinguish between these two models. Here are shown the cases of what are the effects of local environments on the properties of the star-forming stars, what are the IMF, the initial mass function. In particular, on the left, it is shown the initial mass function at different for different masses, and we see that there is an agreement for solar metallicity IMF for high mass stars, that is to say, for masses larger than 0.3 solar masses, while there are large uncertainties in low mass and substellar regime. In the center, it is shown that there are a much lower disk fraction for low metallicity values, lower than 0.2 metallicity of Sun, which indicates a shorter disk lifetime. And in this case, observations, again, of Vesper and Nexus would allow to observe several young stellar objects simultaneously in an embedded cluster with low metallicity. Here is shown this image is the star-forming region in the small Magellanic Cloud, and the blue square represents the field of view of Nexus, while the red is the field of view of Vesper, and simultaneous observation of both young stellar object and extended emission could be obtained. On the right, it is shown the typical emission lines in young stellar object spectrum between 1.8 and 2.4. However, I remind you that SHARP can cover the wavelength range between 0.95 and 2.4 micron. What is the formation of the globular cluster, the origin of a globular cluster, and also the origin of the multiple of the second generation of stars seen in some of them. Basically, this is the image of the globular cluster number 5 in the galaxy Fornax. Superimposed is the field of view of one module of Vesper with six probes. Again, I remind you what is the angular resolution. And basically, this would allow us to retrieve individual stellar properties, kinematics and chemistry, for hundreds of stars at a time to tackle the issue both of the formation, the origin of a globular cluster, and the origin of the multiple stellar population. But this information can also tackle another important issue, whether globular cluster host intermediate massive black holes or not. Intermediate massive black holes are those with masses of about 10 to the 2, 10 to the 4 solar masses, and it is strongly debated their existence. And it is thought that the globular cluster are the most probable loci where search for them. And finally, last but not least, what can be done in the very high redshift universe in order to compare with the local information, with the information derived on galaxies in the local universe. Here is shown a zoom in of a galaxy observed at redshift 10.5, that is to say half gigayear after the Big Bang, observed with a probe of Vesper. And again, this is the angular resolution of Vesper, and we can resolve sizes comparable or lower than 150 parsec in the rest frame of the galaxies, and compare directly this information with those observed in local galaxies. For comparison, this is the angular resolution of NIRSPEC. And of course, Nexus other targets, align them along the slit. So SHARP bridged the observational gap between the nearby and the early universe. What is the prospects of the SHARP project? First of all, our objective is to propose SHARP at the next call, ESO call, Expanding Horizon. The deadline for proposals is June 2027, but by December 2026, a letter of intent must be sent. We propose SHARP as a significant upgrade for an existing facility, which is ELT. For that time, by December to 2026, it is fundamental for the SHARP project to assemble an international consortium, which is fundamental to cover all the know-how needs to carry on such a large and complex project. So we are open to collaboration with potentially interested foreign institutes, and as well as individual researchers. So I invite all of you, or if you are interested, to contact us and to join SHARP. We are preparing a SHARP science book that will be published in New Astronomy Journal. Sorry. The science book will be a collection of scientific cases showcasing the instrument's capabilities in the different areas of astrophysics. And it is not anyone is eligible to submit a scientific case. It is not necessary to belong to the SHARP team, so I invite anyone interested to submit a scientific case, even if you are not interested to join the SHARP project. So SHARP could exceed the observational limits fixed by NIRSPEC at JWST, and would allow us to explore the new path that JWST is opening. So we are convinced that SHARP could take up the baton left by JWST when its mission ends. This is SHARP. Thank you.
Thanks, Paolo.
Thank you.
Okay, any questions or comments for some interactions? Andrew, I will ask you to unmute. Please, Andrew.
Hello, Paolo. Many thanks for your interesting talk. Very interesting concept. Can you actually hear me? Yeah, it's not quite. Yeah, excellent. I see the science case for the high Z galaxies when you kind of talk quite a lot about local volume galaxies, globular clusters, and so on. I mean, many of those obviously have overlapping science cases of other facilities that you mentioned. I mean, you quoted Francois Amer and so on, the former PI of Mosaic. And Mosaic obviously does not only have an IFU, it also has a MOS mode. In addition, there's also moons, things like that. But what I was wondering a little bit more, all your capabilities or intended capabilities are quite nice. Aren't you a little bit worried about complexity, reliability, potential failure stuff? There are moving things in the instrument. You align your slits and whatsoever, and all that stuff needs to be done in cryo environment. Are you not a little bit worried that you're stretching it?
Okay, thank you for the question. Actually, the movement as to the, for instance, the Nexus configurable slit system, the basic system, the bars which move to form the slits is already well established in other cryogenic environment, for instance, MOSFIRE at Keck, but also at the near infrared camera spectrograph and the Grand Tecan in Canary Islands. So there is no complexity actually in that realization. What it is actually challenging is the positioning of inversion prism on each slits. This is a challenge, of course. We are working on this. We have already find some solution, but it's not very compelling and elegant actually, because it's quite simple to imagine to align in a bar some inversion prism with different angle, fixed angle, and you move the bar exactly as you move the bar to form the slit to put the prism aligned to the slit. But this is not, I mean, not only elegant, but also the best way to proceed, since you are not allowed to select an arbitrary angle, but you have to work with fixed angle. The other movement as to the related to the integral field selector, again, are movement, linear movement. Again, it is exactly the same movement of the bars for the configurable slit system. So from that point of view, there is no problem to work in cryogenic environment. And the accuracy, we are working on the accuracy to study through simulations, which is the needed accuracy to match exactly the position of targets. And however, we are room in the scaling factor of optics within Vesper. So we can arrange the mechanic approximation with optics, basically. So we do not see, for the time being, problems in reliability and realization, actually. I don't know if I answered to all your questions.
No, thanks very much. Good luck.
Thank you.
Paolo, you mentioned we can use the sharp to do the rotation curves of the high redshift galaxies. Could you talk it a bit more? How could we do that?
Sorry, how?
How could we do that for the rotation curves and high redshift
Oh,
galaxies. You mentioned in one slide. Yeah.
yeah. Yeah, well, this is an extremely important topic since basically this is the only way we are in essence, derive an estimate of the dark matter fraction in high redshift galaxies without assign a priori an halo, a dark matter halo mass. This is the only way we have to derive empirically a dark matter fraction, assuming that there is, of course, basically a standard cosmology and a standard without invoking exotic gravity relation, I mean.
I think okay. I almost understand. And the second question is that you mentioned the clouds. The clouds is around the 100 PC. Uh, how could we use it? We use the IFU or use the MOS? I think the IFU is better than the MOS for this scale, right?
Yes, I feel it could be better because even if, of course, there is a loss of sensitivity because of the much higher number of optical elements within the IFU with respect to the MOS. But in principle, an IFU is better suited, of course. Yeah.
Mm.
By the way, the multiple IFU allow to sample larger regions simultaneously.
I see. Any other question online? Okay, let me check. Okay, there is no other questions. I will stop the recording, and we see you next time. Yes. Yeah. Many thanks, Paulo. Yeah.
Okay. Thank you very much for giving me this opportunity again. Thank you. Bye.
Thank you.